So last time I spoke about the canonical quantization and Weyl quantization. Let me recall you a few definitions from that. First of all, we work with the Hilbert space H equal to the space of square integrable functions on some space, including space N2, Rn. However, it is more convenient to consider the subspace of rapidly decaying function as Schwarz functions inside this. In that case, we can introduce the Fourier transform f, which sends Schwarz functions to Schwarz functions up to certain coefficients. F of u is a function of new variable psi. It is equal to 1 over, if I'm not mistaken, this coefficient is 2 pi to the power n, integral over Rn, e to the power minus I x psi, u of x dx, if I'm not mistaken. So this transform is invertible. The inverse is given by the same formula, but with opposite sign here. And the canonical quantization, the usual quantization that was used by the founders of this domain, founders of this science, sent every function A of two sets of variables x and psi. So x plays the role of space coordinates, and psi plays the role of momenta. So this is a smooth function. Actually, it should be rapidly decaying, but yeah, it is not convenient to write down all the conditions. So let it be just a smooth function on Rn cross Rn, and the operator, which is associated to A, and when we apply it to U, will give us the composition of the inverse Fourier transform, direct Fourier transform of U, and in the middle we have the multiplication by A. This quantization principle is pretty well widespread. It has lots of advantages. The formulas are pretty simple, although of course we need to deal with lots of analytical problems here. But the main algebraic problem with this quantization principle is that in this case we cannot make sure that the operator associated with the real valued function A is self-adjoint. So this is not the case in this case. This was the problem addressed by Hermann Weyl in the end of 1920s, where he suggested modification of this quantization procedure leading to the following formula. Let me recall this formula. This time I'll expand this Fourier transform and write down the operator as a double integral. So here we go. So Weyl operator associated to A, when we apply it to a function u and compute the corresponding value at x, is equal to the double integral this time over Rn cross Rn. Well, that's clearly encoded here when we have direct and inverse Fourier transform. But here we have a bit more than that. So here we have I x minus y, which is natural, times xi. And of course, we have u of y in the middle. And then we shall have dx, dy, dxi. However, in the middle, instead of just taking a of, I don't know, x comma xi, we take x plus y 1/2 comma xi. So that's Weyl quantization, and it actually verifies the condition that the operator, the joint operator of A is equal to the operator, Weyl operator associated with the conjugated function, complex conjugated function A. Well, let me sketch the proof of this. Sketch the proof. I will meet lots of computational difficulties, but just a sketch. So first of all, we consider the family of operators J sub t. When we apply it to A, it gives us again a function of two variables x and xi, and it is equal to up to renormalization, rescaling by the inverse of t to the double integral over r to n. Well, of course, this can be singular if t goes to 0, but you see, we will deal with t well outside of this dangerous zone, so don't worry. E 2 pi I x minus y psi times A. Here we have y minus t x plus ty. So to say, we have a convex combination of x and y with parameter t. Comma xi dy dxi. If we introduce this operation, then it is easy to write down both the conjugation and the Weyl operator in terms of the usual operator and the operator J. Namely, we have the following. So here it is. Weyl operator associated with A is equal to the usual operator. That is to say, the combination of direct and inverse Fourier transform here, right? Applied to J 1/2 of A. And also, we have the following formula. Sorry? Is there any question? Sorry? Oh. Yes. I integrate over xi. Oh. You're right, it's a bad thing. Bad formula. Let me see. I think it should be eta, I believe. Yeah, something like that. I think it's just, yeah, a misprint, right? Oh. Sorry. The formula is incorrect, right? It's always a problem with the formulas. So, I have a feeling that,
maybe they should,
yeah.
all J should depend on xi.
Yeah. So this is the correct part. This is also correct part. So yeah, I think actually I think it's something like this. It should be eta psi, I think d eta. I think like this should be correct. I'll check it. When I wrote down this formula from the source, I definitely made this slip of hand. Yeah, sorry. Yeah, I think it should be eta. Yeah, because actually.
But then your j is also a function of t.
Sorry.
But then your j is also a function.
Yeah, it is. It is here. Yeah. So we need this formula, and we also need a formula that a dagger, dagger is equal to the operator applied to J1 of A bar. Yeah, what we need. So I think it is easy to restore this J from these formulas, from these properties, but I'm definitely should be more careful when I should have been more careful when I wrote this. Sorry, I check it twice. Okay. But in any case, I think even this formula is not very important, since I already promised it would be sketch. So we have these two formulas, and also we have the evident condition that J of T Js is equal to J T plus S whenever these two are well defined, right? So what do? We have the following formal. Now I have the formal equation to begin with the operator, Weyl operator associated with A, and we conjugate it.
Sorry, in your lecture, JT depend on x, but not depend from psi.
In this formula.
This.
I mean.
It should be because if you define operator of A, so this is.
Okay, but what psi is here? What's the problem?
Yes, and eta is psi in your lecture, and JAT depend on x only.
But I don't understand. It depends on psi. Psi is on the, you mean in the formula, in the text, in the lecture notes.
Yes.
Oh, so that was my slip of hand, right? I don't remember. Okay, let me. I'm sorry for this. Yeah, I need to be more careful. Yeah, I have to check it. I think it should be like this. Psi is actually here, but yeah, if there were no psi, well, yes. If there's no psi, then we need to erase psi here. Sorry. Yeah. Yeah, I'm sorry for the formulas.
Yes.
Yeah, no eta, psi. But again, we have this formal set of equation. We begin with the conjugation, then according to this formula. According to this formula first, right? It is equal to the conjugation of J1/2 of A bar. J1/2 of A without bar, and we conjugate it. Then we use this formula. It is equal to the conjugation of J1 applied to the conjugated complex conjugation of J1/2 of A bar. Now, when we conjugate, when we conjugate the complex conjugation, the complex conjugation descends to A and changes this 1/2 to -1/2 because of this I here, right? So it gives us op of J1 J -1/2 of A bar. And now we use this property, which gives us precisely op of J1/2 of A bar, which is Weyl operator associated with A bar, right? Yeah. Yes. So the left, I need to erase it here, right? Sorry for this. I just make this remark. No psi on the left. Okay. Okay. So that's the formal proof of Weyl property. We consider the composition of two, well, let us say Weyl operators associated with A and one associated with B. It turns out, by direct calculation, one can show that there exists, at least asymptotically, a certain element A star B such that this formula is true. It is actually possible to write down this product A star B in terms of, in analytical terms, in terms of the integral, actually, right? Here it is. We can just say that A star B is a function of x and psi equal to up to some coefficient, which actually I am not going to reconstruct. It should be equal to the double integral over r to n cross r to n of the following expression. So here we have minus 4 pi I over h bar. So h bar is this formal parameter which helps us to introduce this asymptotic behavior, right? Actually, it is not very important, and I think it is not even, it is not actually necessary here. It is just the parameter which allows us to restore the asymptotic behavior after we expand it into powers, into formal power series. Then we have omega of z minus z bar, z prime, z minus z double prime. I think it is possible to abbreviate this to z, right? Just to save the notation a little bit. Times a z prime, b z double prime, dz prime, dz double prime. Again, z, z prime are elements in R to n. And we actually identify R to n with the cross product, sorry, with the Cartesian product of Rn with its dual space. Right, so x is here and psi is here. In this notation, the operation omega can be written pretty easily in the following. Here's the formula. In the following way. So we begin with x psi, and we take its product with y eta. Then, since these two spaces are dual, we have a well-defined value of psi on y and of eta on x, and we take the difference. So actually, it is not necessary to use this omega. I can just write down the formula in terms of this scalar product, actually. But it is more convenient to use this abbreviation because it actually sheds some light on the nature of our construction. So, there is an analytical theory, as probably you remember, which allows you to write down such integrals in form of formal series of certain coefficients. Namely, this can be written as follows. So this is pure analytical construction, and it's pretty well hot analytical work, which is beyond this formula. So we need to take this sum over k from 0 to n, and then add, so inside of inside this sum we have another sum over multi-indices I and j, such that their sum is equal to k. Let me recall you that multi-index is a collection of usual indices. Here we have p. Let's see, I think it should be p. Okay. Sorry. Oh yes, it will be p. J is equal to J1 JQ. P is mod I. Q is mod J. So in total we have exactly k indices, right? Then we have the following expression, -1 to the power mod j, I factorial, j factorial. So I'm not sure I need, this is correct. I'm sorry. It's a little bit, no, sorry. It's, it's more complicated than this. Sorry. Actually, we have exactly n indices here. So yeah, it's a little bit different. It's more complicated. I didn't want to go forth, but so, sorry. Mod I is equal to the sum I 1 plus in. Mod j is equal to j1 plus jn, right? It's more complicated than this, sorry for. Now I factorial is a product of I1 factorial times I2 factorial in factorial, and the same j. Right? Yeah. Then we have this expression, which is pretty, it's already pretty long, you see. So fortunately, we'll be able to cut down all these indices to some very simple expression, which I will show in a minute. But first, I need to write down this analytical side of the story, just to get rid of the analysis once and for all in the future. So here, we need to take the product of this expression with something pretty nasty again. So here we have d xi I partial x j of A times d xi j partial d xy of B. So what is d? What is partial? Dix. It is d mod I over d I1 x1 d I n xn. And what is d I sub xi? It is d I1 xi1 d in xi n, where d xi k is 1 over 2 pi I d xi k. You see it's pretty nasty. So we have this expression, and then in that we need to add the residual term, and that's the analytical side of the story. As you see, it's pretty long, and it doesn't give you exact solution, but it only gives some asymptotic expansion. However, if you look attentively at this first part and forget about the coefficients, which are not very instructive, I would say, we'll see that this can be written in a pretty familiar way. Namely, up to the coefficient, which I'm again going to omit altogether, let us take the following expression in partial derivatives. D over dxi tensor d over d psi I, right, minus d over d psi I tensor d over dxi. This is a bidifferential operator, because this tensor in the middle means that we will apply the left side to the left function a, and the right side to the right function a, b. So if we do this, what we obtain is clearly equal up to some, so probably coefficient, which I'm not going to restore it now. This will be equal to a comma b, to the Poisson bracket of a and b, right? Just in the way I described it. Now, what we can do, we can take this bidifferential operator, d. Let me abbreviate it to something like this: pi ij di tensor dj, where I use single formula di for both partial derivatives with respect to the coordinates and the partial derivatives with respect to momenta, right? And pi is the matrix of this form: 0 here. Here we have, I think, minus identity matrix. Plus. And here we have minus identity matrix. And 0 here as well. So if we use this, so this part actually corresponds to the partial derivatives with respect to xi, and this part corresponds to partial derivatives with respect to x. So as you see here, we have some combination x and xi, and here we have x and xi again, right? So if you write down this formula and check it, you'll get precisely this expression. So if we forget about this coefficient, it will be pretty easy to see that up to this nasty expression with 2 pi I, which actually differentiate this capital D from partial d psi, right? We will have here the formula of the form. So let me take this operator, pi ij di tensor dj, and take its kth power, in the sense that we take separately the composition on the left and on the right of this tensor product. And what we have here will correspond to this expression up to these coefficients, more or less, and up to this nasty 2 pi I, right? But this nested 2πi can be actually totally done without, by just rescaling xi I, introducing it inside these variables, these new variables, so that will not hinder us in any case, in any way. And what we get is this as a general term. Of course, we have 1 over 2 pi, 1 over 2 in the power k. And also we need some formal variable which will somehow indicate the convergence of our series, right? Because here we don't need this formal variable because it was an asymptotic series, and it had some analytical properties. It only had some finite number of terms all the time. And since we want to work with formal power series, we need to introduce this formal h bar to the power k here. And that will be the generic term up to this h, which we can again restore by introducing it into the formal variables, for instance, into x. I don't know. That's not a problem again. Nice. That's a generic formula. And we end up with the following hypothetical formula for the product. So now this formula is just a pure algebraic formula. It has no analytical, meaning beyond it, because I tried to abandon it altogether. We have multiplication on the left, then we have exponential of h over 2 of this differential operator, bidifferential operator, di, dj. And we apply it to the tensor A, tensor B. And that's precisely the Moyal product which we are going to study right now. So that was some kind of analytical side of the story, and I gave some let me say it like this, some intuitive foundation for this formula. Let me give you some, maybe, I don't know, maybe less multiplication. You see, when we take this formally, when we apply d dx to tensor d dy or d dx, I don't know, to a tensor b, we will end up with dA dx tensor dB dy, right? But we need to get rid of this tensor product sign. So this is just a multiplication, which somehow just throws away the tensor product and ends up with just the usual elements in the function.
So we guess this formula. I mean that it's
So,
not obvious why it's equivalent to the formula that is.
This formula, this is actually this. It's just a kind of.
But why there is exponent?
I mean, exponent. We have because of that coefficient, 1 over I factorial, 1 over j factorial. Because of this. It's precisely the remaining part of this coefficient, which, you're right, you need to be more careful than that to see this coefficient. Yeah, the sign is simple, because the sign is just minus 1 to the power mod j, I believe. Right, but mod j is precisely the number of minuses in front of here, which appears here, right? Yeah.
But where is sign?
The sign is incorporated here, because pi. If you write down this pi j di dj, you will see that it is equal to the sum d dxi d. Yes, precisely. Xi I minus d xi I d dxi. So that's precisely this formula. So again, I think I'm running a little bit out of time, so I'll skip this. But it is, if you open these lecture notes, there is I think a page in which I explain how to derive this formula from the original formula for the involving integrals for A star B. So let me recall this formula with integrals, and then you can. It's page 21, I think, in that lecture notes of mine. So we begin with this formula: A star B is equal to, well, certain coefficient which I'm not able to remember, double integral R to n cross R to n, E something like 2 pi I minus 2 pi I by H bar omega z minus z prime, z minus z double prime, right? A z prime, B z double prime, dz prime, dz double prime. We take this formula.
Shouldn't be there minus 4 by I over H.
Maybe 4. It's something I have never been able to remember. But you're right. Before I got rid of 2 pi, my formulas, physicists usually say let us set 2 pi I equal to 1. Yeah, it's possible sometimes. Yeah, but before I have said it, I need to take care of 2 pi. You're right. But yeah, I'm sorry for this. Let me sketch the idea. Then we can actually rewrite this formula using some formal expressions for the delta functions. Delta functions. Actually, one can say the delta function is a Fourier transform of 1. Right? As far as I can remember. This doesn't have any sense. This has no analytical sense, this expression. You see? Because if you do this, the integration, you'll see that the integral does not converge in any reasonable sense. But if you take some formal properties and you try to apply the inverse Fourier transform to delta function, you get precisely 1. No? It's just some easy exercise in this sense. So you can work hard to introduce some analytical sense into this play, but you can regard this formula as just some algebraic kind of game. And then if you use this formula and introduce delta functions here by this formula, to this end you need to expand your integral to quadruple integral over 4-fold Cartesian product of R to n with itself. Then you can change the order of integration. Again, it has no analytical sense because, in order to change order of integration analytically, you need to provide certain convergence properties, which is by all means violated here, So, but still, if you look at this as some kind of an algebraic game, you can change the order of integration and reassemble this integration into this kind of expression. Yeah, you can look at the page, I think 21 in the lecture notes. Okay. If we have time in the end, I'll try to reproduce it, but not now. Now, let us investigate the properties of this formula. The first thing I'll do, I'll generalize it a bit. Just a little bit. So in the original formula, I took pi ij to be very concrete skew-symmetric metrics. Right? But it is convenient to consider a very general formula of this sort. So let pi be any matrix. For a while, not even skew symmetric. It's just a 2n by 2n scalar matrix. Complex or real, I don't even care. It'll be complex. Okay? Then we can still obtain this kind of product. Just to underlie, just to stress the fact that it depends on the choice of this matrix pi, I'll write pi as a subscript in this formula and regard it as a definition. So actually, sometimes people even omit this 2 from 1/2 from the formula. It doesn't make any sense to keep it all the time, because you can incorporate it either in pi or in any of the partial derivatives, very scaling. But let me keep it for a while. And we have pi ij, and di tensor dj. And eventually we have a tensor b. You can regard this so as a map which takes elements in C infinity. Let it be even C to n is okay, but let me just write V for the space. Okay? Space. So A is element here, B is element here. And send it to the formal power series of same kind of things, of functions on V, but with H bar playing the role of formal variable, right? Just this on the right is a space of formal power series. As we discussed it at our seminar last Thursday, right? This can be expanded. To a kind of product from C infinity V H bar, the tensor square of the space, into itself. You remember that actually, if we just take any element in infinity of V tensor with with coefficients in H bar, for formal H bar, and apply this kind of formula term-wise to this formal power series, right? And since the convergence in formal power series only means that the powers of H bar grow indefinitely, right? And we don't have any infinite sum at any finite stage, then of course this expression defines a very nice map of this sort. And it is my purpose now to consider the properties of this map. So the properties are pretty simple, but important. So now this expression stands more generally for this kind of map. So the first property, evident property, is that A star pi 1 is equal to A and is equal to 1 star A. Right? And it's clear because we always have partial derivatives applying both to A and to B. And whenever one of these terms is just is constant, right? Then its partial derivatives vanish. All its partial derivatives vanish, and only the first term in this expression survives. And the first term looks just like the product applied to the 0th power of this differential operator, right? But what is 0th power of anything? It's just identity. So it's just A times B, and there is no problem. And let me write down this observation as this next step. A star B always begin with A times B, right? Let A and B here are just smooth functions. Plus, and then the first term is also pretty easy to find. The first term will correspond to the first power, to the linear term in this formal power series. So it is just the operator pi ij di of A dj b times h bar by 2. So it will, and then I'll abbreviate this expression just to this. Again, A comma B sub pi is the sum of I and j, pi ij dA dxi dB dxj. Here I use the common symbol x both for momenta and for coordinates, just to save the time and save the notation. And it is well grounded, well based, because all the coordinates are the same for me now since I have introduced this matrix. As soon as this matrix is introduced, there is no difference between momenta and coordinates. They're all the same. They're homogeneous in this sense. Right? There's no. So don't take. It would be. It would cost me some. It is not very easy. It would take me some efforts to restore coordinates and momenta from this expression. So this procedure of restoring momenta and coordinates part from the generic bilinear form of this sort is called polarization. So I don't take any polarization. I just use the generic formula. Okay, nice. But then, if we go on, the remaining part is much less evident, but it will look like something like this. We have the kth power of h bar, but then they have some bidifferential operator bk applied to a and b. Right? And the sum is for k from 2 to infinity. Observe that this expression is not, in fact, Poisson bracket yet. It's not even symmetric, and it's not even antisymmetric, because pi is not assumed to be antisymmetric. It's just some coefficient. It can be not symmetric, not antisymmetric. It can be anything. Okay? But still, you can write it down like this. The third property which I'm going to use is much more important, and I'll prove it much more carefully than the previous two. This product is associative. So here is the associativity, and it is defined in algebra. As you see, and we have three functions, a, b, and c. They can take their product in two different ways, take their common product in two different orders. First, we can take the product of a and b, and the result multiplied by c. Or we can first take the product of b and c and multiply the result by a. And it turns out that it is always the same. So let me prove this. let me begin with the following observation. The multiplication of A and B, A tensor B, composed with any partial derivative is equal to M composed with the expression di tensor 1 plus 1 tensor di applied to A tensor B. This is just a Leibniz rule, nothing else. I'm going to use this. I'm also going to use the following observation. If you have some exponential, an exponent of some bidifferential operator with constant coefficients, I don't know, let me write it down just as A. A is a bidifferential operator with constant coefficients. And B is also a bidifferential operator with constant coefficients. Then exponent of A composed with exponent of B will be equal to the exponent of A plus B. And that is clear because when you have constant coefficients, operators commute. It is not always true for generic bidifferential operators. But then they have constant coefficients, they always commute, and we can use this formula. And also, okay. Okay. So let me now compute this. A star sub pi of B star sub pi sub C. It is equal to what? To the product of exponent of h bar half, 1/2 of h bar, pi ij di tensor dj applied to what? To A tensor B star G, B star C, right? Equal to M, exponent of h of pi ij di dj A tensor with M exponent h bar half pi pq dp dq. Oh, sorry, I'm running out of space. Of B tensor C. So now I'm going to push this differential operator across this. What do? First, I observe that this is equal to 1 tensor m composed with exponent of h bar divided by 2 pi pq dp dq, right? Applied to A, tensor B, tensor C. And here we have still m, still exponent of h bar divided by 2 pi ij di dj. Right? I actually can erase this sign because I just rewrite it. I just rewrote it. Yeah, nothing else. So what does it mean that we have this kind of thing applies? So this applies here, right? And this applies here. Sorry, this term applies here. So dj is applied to m, right? Oh, by the way, I just forgot. I can actually still rewrite it before I proceed. Sorry. And I write it like this. This is 1 tensor m composed with exponent of 1 tensor h bar divided by 2 pi pq dp dq. And actually, I can even move it here, right? So let me rewrite it yet a little bit. So it's something like h bar divided by 2 pi pq times 1 tensor dp tensor dq. And this is this, and we can go on. Exponent of h bar divided by 2 pi ij di dj. Yeah, eventually we have this formula. Again applied to ABC. And see, I just rewrite everything. There's nothing I can do. So it only remains to move this 1 tensor m across this operator, right? But if we exponentiate this formula, right, so we take exponent of di composed with m. We have the exponent on the right again. M exponent of di tensor 1 plus 1 tensor dj di, right? If we exponentiate this here, it will just write, it will boil down to the exponentiation of this formula here. It actually just means, if you are physicists, you probably know that exponential of partial derivatives is shift operators. Yeah? So we have a shift operator in direction of the ith coordinate of product of two functions. And here we have, first we shift both these functions, and then the multiplier product. And of course it is the same. It is just this. So here we have, so I forgot to write down m here. So eventually we have this m tensor 1 tensor m. And exponent of h bar divided by 2 pi ij di. And now instead of dj, I need to write this. Di dj tensor 1 plus di tensor 1 tensor dj. And again, I need to continue it with this. I forgot, you need to expand it here, right? Now I have this here is exponent of h bar divided by 2 pi pq 1 times the dp times the dq. Right, and it applied to ABC. So now I have product of two exponential operators of operators with constant coefficients. So I can use the second observation I made, and I end up with the following formula. M composed with 1 times m exponent of h bar divided by 2 pi ij di times the dj times the 1 plus di times the 1 times the dj. And then, since again pq are just summation indices, right? They don't play any role. I can rewrite this as ij, nothing else. Then the third term will look precisely the same way. 1 times the di times the dj. And then it's applied to A times the B times the C. So that's the product taken in this order. That's actually the final result. But if we take the opposite order, the other order, and begin with A times A star B multiplied by C, we'll get the same formula, which will only begin with different composition of products. Instead of taking M composed with 1 tensor M, we'll have M composed with M tensor 1, but then we'll have the same exponential operator applied to the same A tensor B tensor C. And of course, the usual multiplication is associative, so we have this. And it means that it proves the statement. So this product is associative. Very nice. Now, all of you, and especially those of you who have some knowledge of this theory, will probably wonder, it is normal to construct the star products beginning with Poisson brackets. And now, instead of Poisson bracket, I have some other bracket which is not even skew symmetric. How comes that we still have associativity? Well, that's not a problem, in fact. Here is the following property number D. So I begin with A, B, and C. So that's property number C. And the property number D says that even though this product is not associated with any Poisson bracket on the nose, the Poisson bracket still lurks behind the scene, and it is easy to restore it. And that's what we are going to do right now. Before I formulate this property number 3, number D, let me introduce one more piece of notation and definitions. So let A star B and A star prime B. Let it be two operations on functions with values in formal power series. No, I don't even assume that they are associative. So I assume that A, B are formal power series. I'll say that these two operations are equivalent. It's just one possible way to introduce equivalence. I just don't want to go into the most general situation, so I'm going just giving this definition. And if there exists a formal power series T beginning with identical operator, but then I have h bar times t1 plus h squared, h bar squared times t2, and so on, such that t applied to a star b is equal to t applied to a prime star prime times t applied to b. So, since we have discussed this at our seminar last Thursday, this operator is actually invertible. There exists t minus 1, such that its product. Differential operators, you can take products of differential operators. So you can actually take products of two formal power series of differential operators, right? And it will be composition of two formal power series. So using this observation and choosing t minus first in the sense we discussed, we can write down this equation as follows. So it means that T is an isomorphism of C infinity V with H bar equipped with one operation and the same space equipped with the star prime operator. Right? It's kind of equivalence. So that's the equivalence relation. Let now A be a symmetric matrix. 2n by 2n symmetric matrix. Actually, not necessarily 2n, it can be just some matrix on B. And I assume that Aij is equal to Aji. Sorry, Ji. Consider the operator T equal to the exponent of probably H bar. I don't remember if we need 1/2 here, but let it be like this. This is just a differential operator. So it begins with 1 plus H bar Aij di dj plus H bar squared divided by 2 Ai j apq di dj dp dq and so on. Right? Let us consider the way this operator acts on the star product associated with some matrix pi. So let A star sub pi B be acted upon by T. What does it give us? It gives us exponent of h bar A I J d I dj applied to the composition of the product with exponent of pi I pq, it will be pq for a while, dp dq, and everything is applied to A tensor B. So once again, I need to move the product across some exponent of differential operators, right? So now I have di dj, and I need to move it across M. Then it is just a kind of extension of the Leibniz rule. It is M applied to what? To di dj plus di, tensor 1 plus di tensor dj plus dj tensor di plus 1 tensor di dj, right? It's just Leibniz rule, nothing else. And again, since I do this, since I applied this to exponential map, I just exponentiate both sides, and that's what I have. So I can continue this formula. I can go on with this formula, and I have M applied to what? To the exponential h bar aij multiplied by this di dj tensor 1 plus di dj plus dj di plus I think it's okay, 1/2 will play some, right? Will appear still here, but okay, I think it's not worth going back and restoring this 1/2 in its proper place. It will not influence anything actually. But still we have 1 tensor di dj. And we multiply it by exponent of h bar divided by 2 pi pq di dp tensor dq. And apply to A and B. Right? What do we have in the end? Now I have two differential operators, bidifferential operators with constant coefficients. And again, they commute, so the exponential exponents commute, right? And moreover, I can write exponent of the sum of these operators if I really need this. And I do this. I take this piece and this piece from the sum and write down this. So I have M composed with h bar p pq applied to dp dq plus h bar times a ij di dj plus dj di. Right. So it's actually, since aij is actually commutative, this is equal to 2 aij times di dj, because aij is equal to aji. Right? It's just this. But then I have the remaining part. exponent of h bar aij di dj tensor 1 times exponent of h bar aij 1 tensor di dj. And everything is applied to A tensor B. Now you can see that these two terms, these and these, actually give you just T of A tensor T of B when you apply them to this A tensor B. And the first term, oh sorry, I forgot to write exponent here. Exponent. The first term is equal to the exponent of h bar pi ij, exponent h bar times pi ij plus I think I forgot this 1/2 original. It's on stage. And I think you can actually forgive me. I hope you will forgive me this. Because this 1/2 is actually not important. You can implement it, insert it into pi. It will not affect anything. So we can just forget about this 1/2. But still we have 2a ij di dj. So it means that T applied to A star sub pi B is equal to T A T B, which you multiply with respect to pi plus 2a. Respect to this matrix, precisely. But A could be any symmetric matrix. It can actually be not even symmetric, but you see, when we can take this A, I, J, D, I, dj, right? Since these two operators commute, only symmetric part of the matrix Aij survives. The skew-symmetric part disappears. So we can but any matrix can be turned into skew-symmetric matrix by adding a symmetric part of this matrix or subtracting the symmetric part of this matrix. So we can assume, well, that pi is symmetric, skew-symmetric, right? So now I'm ready to formulate a property number D of the Moyal product. So property D every star product sub pi is equivalent to a star product sub pi prime where pi prime transposed is equal to minus pi prime. In that case, we have the property E. In that case, the A comma B sub pi prime is skew-symmetric, of course. And moreover, it verifies the Jacobi identity. You can check it in precisely the same way as before, or you can do this by choosing the good coordinate set coordinate system on the space in which our skew-symmetric matrix takes the form of canonical operator and some zeros, right? And that means that the first term in the Moyal product is actually a Poisson bracket. It means that we can always assume that the first term is a Poisson bracket, since we only consider everything up to equivalence. And also,
Maybe the question is so here, so we found that it's equivalent. This two more products are equivalent using this T, yes.
yeah,
But in this T, we use differential operators, yes.
yeah,
But in definition of the equivalence, we said that T should be a formal power.
it was formal powers, and our C is also
And we
is exponent of h bar a I j d I dj. As you see, it's
and we write when we say that T is formal power series, we write that there can be differential operators.
yeah.
Inside of it.
I mean, this is formal power series of differential operators.
Okay.
A formal power series where each term is a differential operator. That's it. Okay. So, how much time do I still have? I think I'm already running out of time. Oh, 5 minutes. Nice. Yeah, I think I just end with using the following observation, EF. Just writing down this following. But I think because it's, I can actually go on with some other. Yeah, I think 5 minutes is enough for these two things. First of all, number F. Consider BK in the kth term in the formal expression for the Moyal product. Then, according to the expression I have, it looks like up to some coefficient, which I don't care about, looks like pi ij di tensor dj to the kth power, raised to the kth power, and applied to a tensor b, right? Well, and the multiplication is assumed here, mutually assumed. The multiplication of functions is commutative, of course. So when we change the order of a and b, it looks like we just change the indices I and j here. But that turns pi ij into pi ji, which is minus pi ij if pi is skew-symmetric. Right? And when we raise it to the kth power, this minus shows up. And we have the following formula. Minus 1 to the power k, bk of ba. So this additional property is sometimes important for constructing star products, but it is usually omitted in many books. And one more property which I think is important for physicists. Now let us consider complex situation, complex case, complex coefficients. All the complex coefficients. Then our functions f and g will have complex values. Complex. And you can conjugate them. As I explained, the origin of Weyl quantization was from the assumption that complex conjugation actually provides conjugated operator, right? So it boils down to the following formula, which we need to assume. So this is the symbol, in some sense, of some operator of where f and g are operators, are symbols of certain operators which compose to this operator. When we conjugate it, when we conjugate it, a complex conjugation of a symbol, it corresponds to the symbol of the conjugated operator. So in this sense, we should take the opposite order of the composition of the operator corresponding to f and the operator corresponding to g. So it will take us g first, and then f. But both f and g should be conjugated. So we need this formula. If you look carefully here, you will see that this boils down to the assumption that pi ij conjugated is equal to pi ji. So in particular, it means that pi ij should be purely imaginary, right? Because pi ji is equal to minus pi ij, and this is it. So pi should be imaginary. And in particular, you can take pi equal to, well, let me put it like this, inverse matrix of a Keller product, of a Hermitian sesquilinear Hermitian product, a scalar product. So M is imaginary part of a Hermitian scalar product. Is a Hermitian structure. And that is probably all I wanted to say today. So from now on, we will deal with this algebraic side of the story. And our purpose, the purpose of the whole course from now on, will be to extend this construction somehow from vector spaces where we have global coordinates and where we can consider Poisson structures and Poisson bivectors with constant coefficients to non-linear spaces, non-vector spaces, where no such coordinates and no such Poisson structures usually exist. Right? To this end, I'll first describe the theory of Poisson structures and corresponding geometry on general manifolds, smooth manifolds, and then I'll describe the constructions, the quantization constructions, the deformation quantizations constructions by Fedosov and of Kontsevich. Okay. They are not the only known quantization constructions, of course. In addition to the original construction due to some Belgian guys, Lecomte and de Wilde, which appeared first, which was the first to appear in the beginning of 1980s, there exist lots of other constructions which are called, for instance, there exists so-called geometric quantization, where everything is done, where some additional assumptions are made, of course. But under this assumption, we don't just get some formal algebraic structure now, manifold, but we get a representation of an algebra of operators on Hilbert space. One can speak about this. One can speak about the Kirillov orbit method, which is closely related to this geometric quantization, which I believe is this topic, is the subject of the talk today at the seminar in the evening, right? There exist lots of other approaches, So, I mean, whatever I talk about, it will be. There also exist quantizations which involve some some algebraic homological constructions, like I don't know, BRST construction and others. I'm definitely not going to speak about this.